Hi everyone. Today we're going to explore the set of real numbers. So let's look at this Venn diagram to look at what the different sets of numbers are. All of the numbers that you know, everything you've ever heard of, all of this is the set of real numbers. All of these are included in real numbers. There are another kind of numbers, believe it or not, the opposite of real, imaginary. You won't learn about them till probably 11th grade, but let's talk about what these are. Natural numbers are the counting numbers, 1, 2, 3, 4, etc. If you add in a 0 to that set, starting with 0 instead of 1, those are called whole numbers. And then on top of that, if you include negative natural numbers, counting numbers, then we're talking about integers. So see how every set is within entirely the next set? The whole circle is within the next big circle. So we're saying integers includes negatives, 0, and positives. Okay? But there's no decimals or fractions in any of these sets. Rational numbers is what adds decimals and fractions. There's another type of number called an irrational number, and those are different from rationals in that irrational numbers, no matter how you tried to simplify them or rewrite them in another form, could never be written as a fraction. They're non-ending or non-repeating decimals. So let me show you what I mean. Okay, so if real numbers include the set of all rational and irrational numbers, then we need to look specifically at what makes rational and irrational different from each other. And I mentioned on the last slide that rational numbers can be written as a fraction. It doesn't mean that they are when they're given to you. It means that they could be written as a fraction. And so 2/3 is rational. 7.1 could be written as a fraction. It's rational. But also the fact that the decimal numbers in decimal form, rational numbers, are either terminating, which means they have an end, or repeating, which means they have a pattern that goes on forever. So terminating, 7.1, it has an end. It stops. This is 7 1/10. Certainly could be written as a fraction. Now, I have no idea what this is written as a fraction, but I see that there's a pattern after the decimal, and that bar over the 32 means that that 32 keeps on repeating. The same way with this next number, 48.6666, the fact that there's an ellipsis at the end, 3 dots, means that that pattern continues. It goes on forever. And that means that it's rational. So irrational can't be written as a fraction. You won't always know right off, but you can always put a number in Desmos in the calculator and check. You can check to see if the decimal stops or it fills the screen, however much Desmos will show you or whatever calculator you're using, and there doesn't appear to be any pattern to it. You don't know for sure, but generally you can tell. If it fills all the slots allotted for an answer and there doesn't seem to be any pattern like this, you can assume that it's not ending and it's irrational. Also, pi is irrational. Remember pi? We approximate pi at 3.14, and you may use that a lot of times when you're doing math involving pi, but the fact is that pi is an irrational number, and the digits beyond the decimal go on forever in no particular pattern. Now, we know what a lot of those digits are, but the fact is it doesn't end. There is no end to that decimal number. So what if you don't have a calculator? We're talking about radical numbers in this unit. So let's think about whether radical numbers are rational or irrational. I can tell you there's a quick way to know. If you do your factor tree and you have anything left that doesn't pair up, it's an irrational number. If you do your factor tree, and this is a simple one, you probably already know the square root of 36 is 6. That's a regular number. It's not irrational, it's rational. But notice everything paired up, there's no leftovers. Because let's say that was a big number that you didn't know off the top of your head was rational. When you factor it, if there's no leftovers, nothing left unpaired, then it's rational. All right, let's look at these examples. Some of them will be really obvious to you, and others you'll really have to think about. The number 5, it's rational. It's just a regular number. But the square root of 5, right? If I did a factor tree, there's certainly nothing to pair up. That is irrational. 0.9 with the bar over it means that 9 repeats. That's a pattern, which makes it rational. Negative pi. I already gave you that one as an example. Pi is irrational, whether it's negative or positive. Anything that can be written as a fraction, rational. Negative 1, rational. The square root of 36, the square root of 36 is 6. And so this one looks like it could be irrational until you simplify it. And then you see that it's rational. This one, while there is a pattern here, there is nothing to indicate that that pattern repeats. And that makes this irrational. This decimal has an end. There's no bar saying it keeps going. There's no dots saying it never ends. It's rational. 575 thousandths could be written as a fraction. This is rational as a fraction. This is rational as a fraction. This last one is tricky. It is written as a fraction, but you have to consider the square root of 3. The square root of 3 is an irrational number. And no matter what we do to it, even divide it by 4, we're still going to end up with an irrational number. The way that you would decide in a case like this, because you're looking and saying, wait, but you said if it could be written as a fraction, it's rational. Well, there are a few exceptions. So if you have any doubt, if there's anything else going on in the problem or in the number, put it in Desmos and check. Check to see if it results in a decimal that appears to go on forever or that has a pattern to it. You have to decide. So there are some rules for properties of adding and multiplying rational and irrational numbers. If they're both rational, there's no question. Your answer is going to be rational. If they're both irrational, and you're either multiplying them or adding them, the problem is it could go either way. It might be rational, it might be irrational. You're going to have to check on the calculator. If the numbers are different, one rational, one irrational, usually the answer is irrational, but then again, there are some exceptions. I'm going to show you a couple of exceptions to these, but the bottom line is that if it involves an irrational number to begin with and you're adding or multiplying, you need to put it in Desmos and check and decide for yourself. So here's some examples of the sum of rational and irrational numbers. Square root of 2 is irrational, 7/8 is rational. We can't simplify it anymore. It is irrational. All right. In this one, 4 square root 5 plus 3 square root 2, both of those are irrational, and the sum is also irrational. In this case, 2 plus 6 square root 7 plus a negative 6 square root 7, those cancel each other out. We have a positive and negative of the same number. We end up with just 2. So you see, we simplified a problem and ended up with a rational answer, even though we started out with some irrational numbers involved. Let's talk about the product of two irrational numbers. Pi is irrational, square root of 5 is irrational. The answer is irrational. Same thing with this second one, but square root of 8 times square root of 2, you know the rules. We multiply, we get square root of 16. But when you simplify square root of 16, you get 4, and that's rational. So you see, we have an exception sometimes, which is why I say put everything in the calculator. All right, so to do these, some of them you'll be able to do without putting them in the calculator, but I'm going to go ahead and show you how each one looks in the calculator and how to look at your answer and determine rational or irrational. All right, so here I go. These are just the ones from the slide. I put them in. I have a rational number plus an irrational number. And if you look at your answer here, you see this is it fills as much as Desmos will show you, okay? And there doesn't appear to be any pattern, irrational. The same thing here. This was multiplication with pi, rational times irrational. All right, no pattern, and it's filling the whole spot, the whole answer field. Same thing with this one. With this one, all rational results in a rational. Adding two rationals results in an irrational. Adding two irrationals, oh, this is breaking the rule. It's an exception. Look. The positive and negative of the same number, even an irrational number, adds up to 0. And that's rational. So you can't just use those rules and blindly memorize them and say that, oh, the answer is going to be rational or irrational in every case. Something like this is an exception. The next one, rational plus rational. You can see it. It's rational, right? Just a number with a decimal. The decimal ends. Same here. We have two irrationals, but the result was rational because, look at my answer. So you might not have guessed that here. You saw irrational numbers and you think, oh, it must be irrational. But no, in this case, it's simplified to just 4, which is rational. So always look at the answer. For this last one, no pattern. It's filling Desmos. I'm assuming there's no n because of that. It is irrational. In general, if you're dealing with two rational or two irrational, if it's the same type of number, you're going to end up with a rational answer. Not always. There are exceptions. If you're dealing with two different types, rational and irrational, whether you're adding them or multiplying, usually the answer is irrational. But there are exceptions. Always use your calculator to check whether it makes sense that it's irrational or rational. Okay, I want you to try the next 3 slides, 4 actually, this one and 3 more on your own. Pull up the slides yourself and look at them. I'll scroll slowly through them here in case you don't have access to the slides right now. Put your answers on paper and then we'll check them in class.